I think this could be the case, yes, if we have electroosmotic flow, then it's more or less constant and it drops to the sides. I think I saw, yep, the answer was also in the chat. So we do have in pressure-driven flow, we do have this parabolic profile. So it's not constant, you're also right? Ah, okay. So it drops to 0 at the walls, and then you have this parabolic flow profile, which is also called Hagen-Poiseuille flow. And just a quick reminder, it looks the same for all kind of geometries, but of course the velocity is not the same if you use a rectangular or a circular channel, for example. So we were mostly talking about pipes in fluid dynamics in the basic courses, and now we're also talking about rectangular channels because those are way easier to manufacture. You can just mill them. So please keep in mind that while, of course, the same rules apply, the actual function looks a little bit different if you switch from pipes to rectangular channels. So those are the two characteristics we have of flow and pressure-driven microchannels. And just to remind you, the Hagen-Poiseuille equation for pipes looks like this, and the Hagen-Poiseuille relates the volume flow to the pressure drop. Right? This is important to know. This is like the most basic equation from fluid dynamics I wanted to remember, and this also plays a very important role in the layout of pressure-driven chips, because with this formula, if you have a given pressure, you can calculate the flow rates, or you can calculate the pressure you need to apply to the chip system to achieve a specific flow rate. So this is very handy. You don't have to solve all those Navier-Stokes equations. You can just use this formula, as long as you have laminar flow. And for rectangular channels, it looks a little bit different. This is what I just told you. So usually when you manufacture any kind of chip, it's way easier to realize rectangular channels, and then the Hagen-Poiseuille equation looks like this. So instead of the radius, here we have the height and the width of the channel and some geometry factors. And if you want to use this Hagen-Poiseuille, and you will use it in the exercise and probably also at some point in the exam, please be aware that while it does allow you the fast calculation of pressure drops and flow rates, it's only valid for laminar flow. So if you ever encounter something else than microfluidics, or you're not sure if your system is laminar or not, make sure that you calculate the Reynolds number, get an idea how your system behaves, and if the system has laminar flow in it, you can use the Hagen-Poiseuille equation. Also, please know that you don't get the spatial distributions of velocity. So this Hagen-Poiseuille equation assumes that you have this parabolic profile. So if you use this kind of mathematical framework, you cannot expect to calculate any what's this or something else that also can happen in laminar flow. So it's a very basic description, but it's quite useful. And when we are talking about this Hagen-Poiseuille, we also have to talk again about the hydraulic resistance. This is just Hagen-Poiseuille rearranged, and you can directly see that it looks like this. The difference in pressure equals some kind of hydrodynamic resistance times the volume flow. And this hydrodynamic resistance is nothing else but a geometry factor multiplied by the viscosity of your fluid and the cross-section of the channel as well as the length. So this should also be already known from the modeling and simulation part, but this is mostly applied in this lecture and also in the exercise, so please remember this. And as you can see, or what I would like you to take away, is how the fluidic resistance relates to the individual components of this formula. So you can see that, for example, for a circular cross-section, the hydraulic resistance scales to the power of 4. with respect to the radius. So if you decrease your channel width, if you, for example, mill a smaller channel and you then want to apply the same flow rate, you must be aware that the hydraulic resistance scales like this, and you need a much stronger external source. So all those considerations you need to take into account when you apply or when you want to design a pressure-driven network relate to those basic lectures we covered earlier in this course. So how can you now, let's say, lay out a pressure-driven chip? And it's quite easy. We discussed this already. This is the network and fluidic analogy. So if you have a lot of hydraulic resistances, meaning you have a lot of channels which are connected, and they are connected in a series, then you can just perform this simple addition to calculate the equivalent hydrodynamic resistance. If it is a parallel connection, similar to electrokinetics, you just apply the basic rules you should be well familiar with from electrokinetics. Then you have the mass conservation, meaning if a channel splits into two channels, like so you can imagine something like this, and you have the inflow from here, you know that at this point mass conservation holds and the whole mass must be distributed within those two channels. So very basic. And then you also have the energy conservation, meaning that if you do a loop, a closed loop, and you add up all the pressure differences, then they must add up to 0. So this is basic, nothing else but the Kirchhoff laws, which you already know from electrodynamics. And before we start into the real application part, I want you to think about this problem for a moment. So consider this channel network and assume that all the channels have the same cross-section and that the length 1 is given. And what I would like you to do is just take a moment, maybe together in groups of 2 or 3 people, and discuss how you could calculate the equivalent hydrodynamic resistance, and maybe even perform the calculation, which is quite straightforward and can be done with pen and paper. So please take a couple of minutes in small groups and discuss this problem.
I would like it to rotate it and flip it like that. And then to be L2 is equal to 4L1, 2L1, 4L1. So this 4 will become 2L, it is in parallel, but this is the length. This is the length. But the length of the what? Which was all the equal length. Yeah. Which is the current, and so resistance and the resistance. Yeah, cross section. Yeah. What's the pattern? The diameter. Yes, L is equal to Alexander. So, yes, like this one. steps repeating this word. I wanted to tell you when you told me about ice cream and I was like, okay, I'm going to select one. I yesterday by instrumentation. And this one's I didn't say that any of the lectures are related. I keep repeating the lectures and I don't understand and I keep repeating it. And the video just 15 minutes left. It takes like I said the YouTube can just the whole day for one chapter. And I just have 3 videos.
Same situation for my CMOS, you know. Did you do today's exercise or Thursday you come again class?
The exercise, it's fine.
Alright, did anybody come up with a solution already? One. You came up with one? Okay. The other group, do you found a solution?
Three times.
Okay, you came up with 3 times. Alright, so let's look who's right. Unfortunately, it's 3 times, not 1 time H1, because it looks like this. So if you look at this network, you can directly see that you have a parallel as well as a serial connection. So those 3 are in parallel, and then the equivalent resistance of those 3 is in series with this one and that one. So the total hydrodynamic equivalent resistance looks like this. And if you then perform this with the given assumptions, you end up with this term that the equivalent hydrodynamic resistance equals 3 times the hydrodynamic resistance of channel 1. So it's, you just have to follow this guideline, and this will also be covered in the exercise. So there will be plenty of occasions to train this. Any questions regarding the physical mathematical framework, how we can describe or lay out pressure-driven chips? All right, perfect. So again, if you're unsure, always come and ask, and also there's more information in the respective lectures, which would be, of course, fluid dynamics and modeling and simulation. So maybe if you check it, if there are questions, just ask us. So we now continue with some unit operations which are relevant in pressure-driven systems, and I don't want to cover all of them, so I just picked a few of them which show some interesting concepts. So we start with mixing, and we start with a very special type. We start with the Dean mixer. And basically this Dean mixer, or this mixing principle, is based on the idea to generate secondary flow patterns in channels. So what does it mean? Just a few minutes ago we talked about this pressure-driven flow. So you know how the flow profile looks. The flow profile will look like so this is your channel, and you apply some pressure, you will end up with a flow velocity profile which looks like this. So you can imagine that, for example, if you have one channel entering here with liquid 1 and here with liquid 2, and you will have some interface here, and now those 2 liquids just follow this velocity profile, right? So there will be very, very little mixing, because the liquid will be transported in the general direction of the channel. So usually you have diffusion, which helps to mix, but this is kind of slow. So what the basic idea behind the mixing approaches I'm going to show you is that we want to generate some kind of secondary flow pattern, meaning that we superexpose another flow field onto this fluid, so it starts to mix, we form vortices and so on. And this is what I mean with the generation of secondary flow patterns. So you somehow have to break up the typical Hagen-Poisson profile, and this is in the D-mix approach done by a very simple trick. Here you can see the channel. So this is like the cross section here, and you can see that it is somehow bended, right? It's a curved microchannel. And what happens now in a curved microchannel when you apply pressure-driven flow is that those secondary flow patterns are generated. Because, so here you can see top view. So here you can see from the top how the flow velocity would look like, and here you can see it from the side. So this is Hagen-Poisson, and by pushing it through a bent channel, which is also illustrated here, you induce some kind of counter-rotating vortices. So here in this image, you look at the cross section. So superimposed on this Hagen-Poisson profile, you get two counter-rotating vortices, and those vortices lead to this kind of flow image where you have this kind of swirling, so the two liquids would start to mix. Okay, so this is a very basic concept how you can enhance mixing in pressure-driven chips, even though the source you apply will always lead to this very laminar Hagen-Poisson flow where you don't have mixing. By just arranging your channel in a very clever way and making use of this bended curve structure, you can enhance mixing. Alright, and please be aware that this is still laminar flow, right? We don't have turbulence here, it's purely laminar, but of course, you could also describe this with Navier-Stokes, but it's way harder to describe. So usually you get those kind of images with CFD simulation. But still it's laminar and not turbulent mixing. And the second approach, which uses basically the same principle, and which is very common in pressure-driven systems, is a staggered herringbone mixer. And it also relies on the same principles. So again, we want to create those secondary flow patterns, and this is achieved by not having a smooth bottom, but we have those kind of ribs you can see here, and those ribs induce some complex pressure field, and this pressure fields then lead to the formation also of vortices. You can see this here. So here, this is taken from a paper. It is illustrated at the very beginning, before you have this additional mixing area. Your flow looks like this. So you have the black area here, and then you have the white area here. And due to those secondary vortices, your colored area is being moved up and slowly transported in this kind of vortex. And here you can see a second example where the structure is even more complicated. So you have this kind of arrow shape, and here you can see that highly complex flow characteristics will form. And the aim of this is that you increase the area of the interface between the two liquids. And if you increase the area of the interface, you have more diffusion, basically. Okay? So using just hydrodynamic principles or using some kind of geometric features like bending a channel or making the geometry size slightly more complicated, you can induce some irregularities to the flow field, so you don't have pure Hagen-Poisson flow, but those vortices, and that this leads to enhanced diffusion or let's say mixing by convection. Alright, so those are two very common used methods to enhance mixing in pressure-driven systems. Yeah.
Can you put the reference to the math for that?
Sorry?